Okay, so the first example of finding Nash equilibrium in common value auctions that I wanted us to consider is that of a second price auction with two players. So remember that a second price auction is one in which the winning bidder, so the person who bids the highest amount, pays the second highest price. That's why it's called a second price auction. So I want you to assume that there are two players. I also want to make the assumption that Ti, which is the signal that each player receives, is generated from a uniform distribution between 0 and 1, and that Vi, which is the valuation that each player receives from winning the good, is equal to alpha times Ti plus gamma times Tj. Now, you have each player receiving identical valuations only when alpha and gamma are the same number. Otherwise, these values are just simply correlated and not the same value for both players. What I want us to be able to show is that this bidding function is a Nash equilibrium. And the way that we're going to do this is that we will first assume that player 2 uses this bidding function. Using that assumption, if we can show that player 1's best response also looks exactly like this, is this bidding function, then by symmetry we know that player 2's best response to player 1 playing that would also be a bidding function that looks like this. Therefore, following this bidding function would be a Nash equilibrium. So that's what we're going to do now. So we suppose that all types of player 2 bid in this manner, where B2 equals alpha plus gamma times T2. Then we need to know three things in order to know player 1's expected payoff from this game. One is that player 1's, the probability of player 1, this is probability, that player 1 wins while bidding B1, that is equal to the probability that the bid B1 is greater than alpha plus gamma times T2, which is equal to the probability that T2 is less than B1 divided by alpha plus gamma. And now we know that T2 is generated from a uniform distribution between 0 and 1, which means that the likelihood that T2 lies between 0 and B1 divided by alpha plus gamma is equal to B1 divided by alpha plus gamma. And so the probability that P1 wins, player 1 wins while bidding B1, that equals B1 divided by alpha plus gamma. The next thing we need to know is the expected value, so this is expected value, of the payment that player 1 has to make, conditional on, which is this line, given that, or conditional on, player 1 winning. So if player 1 wins by bidding B1, let's say, player 1 wins by bidding B1, then the likelihood of player 2's, then the expected value that player 1 has to pay will be player 2's bid, given that given that player 1 won, which means that B2 is somewhere between 0 and B1. And because B2 is following this distribution and T1 is uniformly distributed, the expected value of B2, given that it lies between these two values, will just be B1 divided by 2. We're heavily exploiting the fact that we know that T1 is drawn from a uniform distribution. So here too, we know that the expected value of B2 is B1 divided by 2, simply because B2 will be following this exact formula. T1 itself is uniformly distributed, so that means that B2 will be uniformly distributed, except that B2 will be uniformly distributed between 0 and alpha plus gamma, because T2 is uniformly distributed between 0 and 1. Okay, if this is not clear why this is B1 by 2, ask me during the Zoom lectures or Zoom office hours. Okay, this is the expected payment that player 1 would have to make, conditional on player 1 actually winning. We also need to know what the expected value of the signal that player 2 has received will be, conditional on player 1 winning. Now, if player 1 wins, right, that means that T2 lies between 0 and B1 divided by alpha plus gamma. And again, we're going to exploit the property of uniform distributions that if T2 lies between these two values, then the expected value of T2 will be just half of it. So that's why we have 1/2 of B1 divided by alpha plus gamma. Now we can evaluate what player 1's expected payoff will be from playing this game and choosing a bid B1. If player 1 chooses a bid B1, then player 1 wins with a probability B1 divided by alpha plus gamma. That's the probability of player 1 winning. If player 1 wins, then player 1 gets the expected value, so V1 minus what player 1 would have to pay, which is this. Right, V1 is just alpha times T1 plus gamma times T2. The expected value of T2 here is this, so that's just this plugged in here. And then this half B1 comes from the expected payment that player 1 would have to make, conditional on player 1 actually winning. And once we simplify this expression, we can show by taking a first order condition that it would get maximized at B1 equal to alpha plus gamma T1. And that, after that, it's just symmetry, and then that concludes our proof. So that square is just another way of saying QED, quadrat demonstrandum. Well, we have shown what we set out to show.